So in the chapter one, we're talking about the mathematics of solid mechanics. The part one is the Cartesian tensors. So what is tensor? What is tensor? Tensor actually is a multi-dimensional array. It's a multi-dimensional array. It uses to describe the function with the local variables. For example, like a scalar. A scalar is a zero order tensor. And for a vector, it's a first order tensor. Or we describe a matrix. A matrix is a second order tensor. So first zero order, first order, second order. Then we can see there is like a AI prime equals QIP dot AP. It means the dimension P will be eliminated. There is only I, this dimension here. Then there is only a variable. It means there is only a direction. So if AI prime is a vector. However, when we're talking about AIJ prime equals QIP dot QJQ dot APQ, it means the PQ will be eliminated by the PQ in Q tensor. The Q tensor might be a transformation, like a transformation matrix in the stress or strain analysis. And then we can make the dimensional becomes the multi-dimensional condition, like the AIJ K prime equals QIP dot QJQ dot QJR dot APQR. It's a third order tensor. And then, according to the definition, a scalar is a zero order tensor. A vector is a tensor of order 1. And a matrix is a tensor of order 2. We just talking about the Qij, this second order tensor. It denotes the cosine of the angle between the xi prime axis and the xj axis. Just like the equation 1.2. If Qij equals cosine of xi prime xj prime, it means this angle of cosine is the angle between xi prime, the axis xi prime and xj prime. So when we talk about the transformation between the different coordinates. For example, like the Cartesian coordinate has been rotated. The Cartesian coordinates x1, x2, x3 are rotated to x1 prime, x2 prime, x3 prime. Then there is an angle. There is an angle between the from the transformed coordinate and the original coordinate. So we can describe the relation between the transformed coordinate and the original coordinate, like a Q matrix. So in the tensor form, it will be EI prime equals qij dot ej. ej is the original Cartesian coordinate. Ei prime is a rotative coordinate. Okay, furtherly, we talk about phi, a scalar field phi in 3D space. Oh, we talk about it later. At first, we talk about the tensor component can be expressed is when a scalar field equals A over S1, S2, S3. It means it's a scalar field, it's a scalar function with 3 variables. And a vector AI equals AI over S1, S2, S3. It means this vector has 3 variables. Like this, and Aij is a matrix with 3 variables. So there is another important concept like a AI, comma J. It means AI is divided by like the xj, like delta AI delta xj. Because there are 2 dimensions, so it's a matrix form. AI, comma J is a second order tensor. And then we talk about scalar field function phi with respect to direction s. Actually, the s is a distance. So when we talk about the scalar field in a 3D space, and there is a path the scalar field, and we describe the location variation. Like a vector r becomes a vector r at d vector r. Then we know that d vector r is the difference between the location 1 to a location 2. And so we need to talk about the distance. The distance of the difference is ds. And the scalar field, when the scalar field is divided by s for first order, it can be developed with a differential Leibniz differential series like this. So it describes the s, y, z. All of these are the function of s. That's an important concept. We will use this concept later. Okay, so we develop the vector r at delta vector r. It equals vector r at delta vector r delta s ds. And we can describe the delta r delta s as dx ds dot I at dy ds dot j at dz ds dot k. It's a vector. It is a vector from the location 1 to location 2. This unit vector is called vector n. And so we can transform the equation 1.7 as delta phi delta x delta phi delta y delta phi delta z dot d vector r ds. And then the gradient of scalar field. In this condition, we describe the gradient of scalar field as differential operator dot phi equals delta phi delta x add delta phi delta y add delta phi delta z. The operator, the differential operator is also called scale, and this is its partition form. So there is another important concept in engineering mathematics is divergence and curl. Divergence and curl. And divergence in engineering mathematics, divergence of a vector can be described like this form. It's the vector delta delta x delta delta y delta delta z dot fx fy fz if the vector f equals fxi add fyj add fzk. So when the vector f the divergence form of the vector f is a scalar field. When we talk about the curl of vector can be determined by the determinant. The first row of determinant is ijk. Second is delta delta x, delta delta y, delta z. The left row is fx, fy, fz. It will become a vector to describe the rotated form of this vector. So we just talked about the gradient of a scalar. It's a differential operator dot phi. If we describe it as the tensor form, it was phi comma I dot vector ei. And the Laplacian of a scalar is the divergence of a gradient of phi. It equals phi comma ii. Divergence of vector is the differential operator dot vector u equals ui comma I. Laplacian of the vector equals ui comma kk vector ei. So we can demonstrate several important concepts. Several important concepts in engineering mathematics like that by the divergence and the curl product. So we won't talk about too much about this formula. You just know all of this equation, and we will use it later. And the most important thing we need to talk in this chapter is orthogonal curvilinear coordinates. So when we talk about the orthogonal curvilinear coordinates, we will talk about the three types coordinates is Cartesian, coordinates and cylindrical coordinates and spherical coordinates. So why the transformation of the coordinate is so important? Because in a infinitesimal form, when we talk about the infinitesimal element, we need to know the stress on the different phase. Like we are calculating the Mohr circle. Like we are calculating the Mohr circle, it turns to the different angle, and we know the stress on this phase. It's also the same concept. If we want to know the stress or like the principal stress or principal strain, we need to calculate the stress or strain on different phase. So in this calculation, we will use the rotational metric to calculate it. And first, we talk about the cylindrical coordinate. If we use the cylindrical coordinate to describe the location vector, is r dot vector r at z vector ez. And when we transform into the Cartesian coordinate I, j, k, is sorry, I just write wrong here. It's r cosine and is r sine and is zk. I got wrong here because we can see this from this diagram. The vector on the x-axis is r cosine theta. The vector on the y coordinate is r sine theta. So yeah, I got wrong here. And then the second one is spherical coordinate system. We can describe the location coordinate as vector r equals r dot vector er. When we divide it as Cartesian coordinates, is r sine phi dot cosine theta I at r sine phi dot sine theta j at r dot cosine phi k. It's a spherical coordinate system. And then in the engineering mathematics, we just talk about the ds, the distance of the path from the location 1 to location 2. When the difference is very little, is just a little, we can describe the differential distance is ds. The square of ds equals hu dot du square add hv dv square add hw dw square. It equals the dr dot dr. So so there is an important tool. It's called scale factors. So what is the scale factor? Scale factor is vector r. Is a vector r differentiated by the u, and the vector r differentiated by the v, vector r differentiated by the w, and all of these are the positive value. And what is UVW? UVW, we can know it from the figure 1.5. When we transform the matrix from the Cartesian coordinate. It like we assume it is vector EU, vector EV, and the vector EW. So there it is. Vector R equals xi at yj at zk equals u vector EU at v vector EV at w vector EW. So how can we transform two equations and make it the same? The key parameters is scale factors. So from the above, the vector EU equals vector R differentiated by U once first order and divided by its positive value. And in the same way, we can get the vector EV and the vector EW. So according to the differential Taylor series expression, C vector R can be described as this form. And then we can get an important conclusion, Jacobian matrix. Jacobian matrix is another important tool in the engineering mathematics to describe the transformation between curvilinear vectors and the partition vectors. We just talked about it in the chapter part 2. X equals the function of UVW. Y equals the function of UVW. Z also equals the function of UVW. Then we using the Leibniz calculator, we can get all of these equations, and we make it as the matrix form. We can get Jacobian matrix. It's called the Jacobian matrix. In summary, the unit volume, actually this volume is an infinitesimal element volume. On the location vector can be calculated by the scalar vectors. It's also the determinant of Jacobian matrix. It's just like this. And I describe again. It'll be like this. This direction is delta vector R, delta V dV. This direction is delta vector R, delta dW dW. This direction is delta vector R, delta U du. So when we cross, sorry, I just so wrong. It's here. It's here. So when the delta vector R delta V dV cross the delta vector R delta W dW, the direction will become the U vector EU direction, and cross and dot with the vector R delta vector R delta U du, it will become the HU dot HV dot HW, and the y dimension is du dv dw. It equals the determinant of Jacobian matrix, that's du dv dw. So why should we calculate the dv? We will apply it like the finite element. Finite element method. Or we calculate the Gaussian elimination theory, like the vector f plus vector n dA equals is a closed integral. Then it equals the 3D integration of differential operator cross vector f dv. So when we calculate the dA dv in a different coordinate, we will use the Jacobian matrix. So let's go back to the scalar field phi. Now we assume that it's a function of UVW, and the vector R is the location vector. Then the phi can be depicted as, sorry, I got wrong again. Actually, it's d phi equals gradient of phi dot d vector R. D vector R, from the calculation later, d vector R is HU dV U dot vector EU at HV dV dot vector EV at HW dot dW dot vector EW. So if we assume the vector gradient of phi is up vector EU dot at vector EV at gamma vector EW. We need to pay attention on here. It's gamma. It's not the vector R. We need to make it clear. Then the d phi can be assumed up dot HU du at beta HV dV at gamma dW HW dW. So in summary, the gradient of phi can be written as 1 HU delta phi delta U vector EU at 1 HV delta phi delta V vector EV at 1 HW delta phi delta W vector EW. This equation 1.25 is very important. When we calculate the Cartesian coordinate, spherical coordinate, or cylindrical coordinate, or any other curvilinear coordinate, we can use this gradient to describe the scalar field in any coordinate, in any orthogonal curvilinear coordinate. And we will use this tool later. So the application of divergence and curl in curvilinear coordinates are like below. We will demonstrate some kind of important equation here. The gradient of U equals 1 HU dot vector EU, and we get the same direction, the same conclusion like the gradient of V, gradient of W, and then we can get the gradient of V cross gradient of W equals vector EU divided by HV HW. Then we can get the question 1.27. Is vector EU equals HV HW gradient of V cross gradient of the gradient of W. And we can get the vector EV and vector EW. So what should we calculate about this? In engineering mathematics, we can calculate the curl and the divergence of vector V in curvilinear coordinate UVW. Then we assume the vector V is VU vector EU, VV vector EV, VW vector EW is like this. So the divergence of vector of divergence of vector V, we can describe it as by the scale factor like this. Furtherly, the cylindrical divergence and spherical divergence are shown as like this form. We at first we must know the HU, HV, HW of cylindrical coordinates and spherical coordinates, respectively. On the other hand, the curl calculation of curvilinear coordinates can be represented as this. The cross of VU vector EU here equals 1 HW delta VU HU delta W dot vector EV minus 1 HU HV delta VU HU delta V vector EW. Then we can get the cross of VV vector EV and the curl of VW vector EW. So in summary, we can get important inclusion. The curl of a vector V we can calculate by the determinant. The determinant is 1 HU HV HW. That's the determinant of this. The first row is HU vector EU, HV vector EV, HW vector EW. The second row is the first the operator. The differentiation of U, the differentiation of V, the differentiation of W. The last row is HUVU, HVVV, HWVW. Then we can demonstrate the curl of cylindrical and spherical coordinate respectively. Then we use the HU, HV, HW applied on the cylindrical coordinate and the spherical coordinate. It's just like that. According to the divergence and gradient demonstration previously, we can demonstrate the Laplacian scalar phi s. It means the divergence of gradient of phi equals like this form. And thirdly, we can calculate Laplacian of scalar in the cylindrical coordinates and the spherical coordinates will be represented as the equation 1.36. So all of these are very important things in the engineering mathematics and improve your basic concepts like the solid mechanics and the fluid mechanics. All of these concepts are very important. So all of this is chapter 1, the content of the chapter 1. Thank you for everyone.